Welcome to Engineers Mindset. Alright, so to follow up our series on Macaulay's method of beam deflection, let's say we have the problem on the board. It says a beam AB of span 4 meter is simply supported at the ends and is loaded as shown. Okay, question says determine deflection at C. Next question says determine the maximum deflection, and finally slope at end A. So we're given the Young's modulus to be this 200 by 10 to the power of 6 kilonewtons per meter squared, and then we're given moment of inertia to be 20 by 10 to the power of minus 6 meter 4. Okay, so this is the beam. As usual, of course, we need to obtain the reactions at point A and also reactions at point B. Okay, so let's simply call this reaction simply RA, or let's start with the free body diagram. So if we look at this beam now, we see that this beam is actually carrying a uniformly distributed load between point C and point B. So there is a need to convert that UDL to simply what? A point load. And of course, we employ the theory we know from shear force and bending moment just to convert this UDL to a point load. So we'll bring back the beam. We have this. Okay, so at point A, we have the reaction at A. Let's simply call this support RA since it's unknown. At point D, we have 20 kilonewtons acting downwards. So we simply have here 20 kilonewtons. All right, so between C and point D, sorry, this is point D. Between C and B, we have a UDL. And I said to convert a UDL to a point load, simply multiply the UDL load towards the length covered by the UDL. Now, the UDL length is actually 2 meters, and the UDL load itself is simply 10 kilonewtons per meter. So to convert this to a point load, we simply would multiply 10 by 2. That simply gives us 20. That becomes the point load of the UDL. Then placing this point load now on the beam, it has to be placed at the middle of the length covered by the UDL. So if the length of the UDL is 2 meters, the middle of 2 meters is simply what? 2 divided by 2, which is actually 1. So that means we have this point load somewhere here. Okay, somewhere here. The value is simply what? 10 times 2, which is 20 kilonewtons. So it's actually what? 1 meters apart. 1 meters apart. So you have this. Not forgetting between D and C is also 1 meter. Okay. Same thing here, between A to D is also 1 meter. So we have this. So this simply becomes the free body diagram. So this helps us now to find this reaction at point B. Of course, there's a reaction here. This is point B. So this helps us to find the support at point B. Let's call this support simply RB. All right, so to find this support, we employ our equilibrium equation. Sorry. To find the support, we employ our equilibrium equation, and the equation simply states summation of the entire force, vertical force acting on the beam is simply equal to 0. We consider vertically upward forces as positive, while vertically downward forces as simply negative. So we start summing up. At point A, we have RAY pointing upwards. Sorry. At point A, we have RAY pointing upward, so it's positive. We simply have RA, okay? At point D, we have a 20 kilonewtons force acting downward, so it's negative. You simply have minus 20. At this point, that's the UDL load now, we have 20 kilonewtons force also acting downward, so it's negative, minus 20. And finally, at point B, we have RB pointing upward, so that force is positive, simply plus RB. The whole of this force, according to the law, is equal to 0. Okay, so you simply have RA now minus 20 simply gives us minus 40 plus RB, and this is simply equal to 0. So all we do now at this point is simply send minus 40 over to this side of the equation. Negative sign crosses an equal to sign becomes positive. So I'm simply left here now with RA plus RB equals 40. So let's call this equation 1. Okay, so at this point now, equation 1 actually consists of two unknowns, which is very much impossible for us to solve. So we employ the second equilibrium law, which simply states that the moment of force about a point is equal to 0. So we simply take moment, and I said if you're taking moment, simply take moment about the point where we have at least an unknown. Okay, because moment is simply force times distance. So if we're taking moment about an unknown point, it means that force multiplies the distance at that point. And since there's no distance between the unknown force and that point, it simply becomes force times 0. That automatically becomes 0. So we can use that now to obtain the remaining what? Reactions. Okay, so we can take moment either at point A since we have an unknown here, or you can choose to take moment at point B since we also have an unknown here, so that the moment of each of these forces at that point becomes 0. Okay, so let's do that now and see point B. Okay, so let's take moment at point B. Let's take moment at point B. Okay, so moment at B, okay, is equal to sum of the entire moment at point B, simply equal to 0. So we're considering clockwise moment to be positive and anti-clockwise moment to be negative. So let's start with this force here, the 20 kilonewtons force. The moment of this force about point B, first of all, moment is force times distance. Distance it takes this force to get to point B is simply 1 meters. And then this force is acting downwards, which means it will turn about this direction to take moment about point B. And this direction happens to be what? The anti-clockwise direction. So which means the moment of this force about point B is actually negative. And each moment is simply 20 times 1. Distance it takes for this force to get to point B. Okay. So we simply have that to be 20 minus 20 times 1. Now minus because it is anti-clockwise. Same thing happens here. I have a 20 kilonewtons force here acting downwards. It means the moment of this force about point B is going to also turn towards this direction. It goes all the way to this point, okay, which is also what? Anti-clockwise to our direction. So that the moment of this force is actually what? Negative. The total distance it takes this force to get to point B is simply 1 plus 1 plus 1, which is actually 3 meters. So we simply have the moment of that force to be minus 20 multiplies by 3. Finally, we consider the moment of this reaction here, RAY, or RA, sorry, at point B. This force is pointing upwards, which means its moment will turn about in this direction, simply going from this point to point B to take moment. And this is actually what? Clockwise to our assumed direction. So that moment is a clockwise moment. And distance it takes this force to get to point B is actually the total length of the beam, which is 1 plus 1 plus 1 plus 1, and that is actually 4. So the moment of that force is simply plus RA times 4, and this is equal to 0. Okay, so if we evaluate this moment now, minus 20 times 1 simply gives us minus 20. Okay, minus 20 times 3 gives us minus 60. All right, plus this is 4RA equals 0. Of course, here minus 20 minus 60 simply gives us minus 80 plus 4RA equals 0. So all we need to do now at this point is simply send minus 80 over to this side of the equation. Negative sign crosses an equal to sign simply gives us positive. We are simply going to have here left 4RA equals 80. So to make RA a subject, we simply divide both sides by 4. Therefore, the reaction at point A is simply 80 all over 4. This simply implies that RA is actually 20. That's 20 kilonewtons. So this gives us reaction at point A. So having found this support now, we can now substitute this reaction where into equation 1 to find reaction at point B. Okay, so substitute RA into equation 1. Okay, into equation 1. If we do that, we simply have, in place of RA now, we say RA plus RB. So in place of RA, we simply put in a value as 20. So it becomes 20 plus RB to be equal to 40 kilonewtons. So therefore, we make RB subject by simply sending 20 over to this side of the equation. Positive sign crosses an equal to sign becomes negative. So we simply have RB equals 40 minus 20. So this also implies that the reaction at point B is also 20 kilonewtons. So that helps us to find the reactions at the support. So we can now what? Fall back to the original beam and what? Institute this support, put back this support into the original beam and not the free body diagram. All right, so let's do that and see. All right, so having known these reactions now at support A and support B, we simply put in their values. RA is 20 kilonewtons, so it means here we have 20 kilonewtons. Also, RB is 20 kilonewtons. It means that here as well we have 20 kilonewtons. So we can now employ the Macaulay's method to carry out this beam deflection analysis. Now I said, using the Macaulay's method, we consider a section. So you section in such a way that the entire load on top of the beam is considered apart from the last point on the beam. And the last point on the beam, starting from point A, the last point on the beam is simply what? Point B. So you section to the last point, at least before the last point on the beam, you carry out this section. And you consider the distance from point A to the point of section to simply be what? X. So if we do that section now, it means let's cut somewhere around here. This is the section XX. And we are simply saying let distance from point A to the point of section remain X, which is this X. All right, so I said at this point, what now is the distance of each of the points about the point of section? Now, to find distance of point D about the point of section, simply was take away the distance we don't need. Since we are now at point B, we want to find the distance of this force, 20 kilonewtons, about the point of section. That is simply from this point to point to XX, which is the point of section. We need to obtain this distance. So I said, if from point A to the point of section is X meters, now I am at point D, which means I no longer need what? Point A. So the distance of point A, take it actually what? Away from what? X. So we simply remove the distance from point A to D away from X. Since I'm moving from point D to the point of section, it means I no longer need what? This 1 meters behind D. So that will give me the distance from point D to the point of section. And that is simply what? X minus 1, because distance behind point D is simply 1 meters. Therefore, distance from point D to this point of section is simply X minus 1. Next thing to do is, what is now the distance of this UDL? Because I've taken the section now, and between point C to the point of section, there is a UDL. What is now the distance of this UDL about the point of section? That is distance from point C, okay, to the point of section. What is now this distance from point C to the point of section? That gives you the distance of the UDL about the point of section. Okay, so to do that, same thing, since I am now at point C, it simply means every other distances behind, I no longer need them. And behind point C, I have 1 meters and 1 meters, which is actually what? 2 meters. Simply what? Take away 2 from X. That gives you distance from point C to the point of section. So I will simply have here to be X minus 2. So X minus 2 now becomes the length of this UDL about the point of section. So we can now take the moment. So therefore, moment about XX is now equal to, now according to Macaulay, you start from the beginning of the beam. The moment of this force, 20 kilonewtons, about the section is simply 20 times distance it takes to get towards the point of section, which is XX. And that distance from point A to the point of section is simply what? X meters. Therefore, the moment of this force, 20 kilonewtons, about that point, simply gives us 20x. And I said that, according to Macaulay, always consider upward forces to have positive moments and downward forces to have negative moments. So this force is pointing upwards. Its moment is automatically positive. Now, from point D, we have a 20 kilonewtons force acting downwards. But this force is acting downwards. So since it's acting downwards, it will have what? A negative moment. And moment is simply force times distance. The moment of this force about the point of section is simply this force, which is minus 20 times distance it takes this force to get to the point of section. Here it is given as X minus 1. So you simply have times X minus 1. Okay, so don't not forgetting you put in your Macaulay's bracket. So after the very first moment, introduce the Macaulay's bracket before the moment of the second load. Okay, after this as well, we introduce the Macaulay's bracket as well. So you put in that bar. Now we need to take the moment of this force. This is a uniformly distributed load. The length of this UDL is x minus 2. So which means, first of all, this load is acting downwards, so it's going to have a negative moment. But then, remember, you have to first of all convert a UDL to a point load before you can take moments. At this point, it's still a uniformly distributed load. The value remains 10 kilonewtons per meter. And to convert a UDL to point load, what do? Simply multiply the UDL load to what? The length covered. If the length covered here is x minus 2, it means now that the UDL load becomes simply minus 10 minus, because it is acting downward, times x minus 2. This becomes the UDL load and not the moment. Moment now is force times distance. This is now the force. The distance now, remember, once you convert a UDL to a point load, let's say this is the point of section XX, and distance from point C, this is point C. Distance from point C to the point of section for this UDL is simply what? X minus 2. So you have this distance to be x minus 2. Okay, this is the point of section XX. Now we've converted this load to a point load, this UDL to a point load, by simply multiplying the UDL 10 by the length covered, x minus 2. I said, after this, the next thing to do is simply what? Place this point load at the middle of the length covered. The middle of the length now simply means x minus 2 divides by 2. So that is where this point load now will act. This point load we found here, we simply have, remember, 10 times x minus 2. This is the point load. Is now acting at the middle of the length. So if the length is x minus 2, therefore middle of the length is simply what? X minus 2 all over 2. Same thing here, x minus 2 all over 2. This is where the point load now is found, at the middle of the length. Now, I want to take moment of this force about the point of section. Remember, the force now is 10 times x minus 2, which is what we have here. Therefore, the moment of this force about the point of section is simply what? This force times distance it takes this force to get to the point of section. And that distance is simply what? X minus 2 all over 2. So it means I'm still going to multiply this force now, 10 into x minus 2 by x minus 2 all over 2 before you can take moment about the point of section. So not forgetting that, okay? I will take this off now. All right, so that means the moment of this force now becomes times x minus 2 all over 2. So that becomes the moment about that point. Okay, so you may wish to want to break this down a bit. Moment about xx is now equal to, we simply have 20x, okay, put your Macaulay bracket, minus 20 into x minus 1, okay, Macaulay's bracket. Now this simply becomes 10 minus 10 all over 2. Of course, x minus 2 times x minus 2 simply gives us times x minus 2 all squared. So I have this, okay. So it means moment about the section is now equal to, this is 20x, okay, put in your Macaulay's bracket, minus 20 into x minus 1, put in your Macaulay's bracket, minus 10 divided by 2 simply gives us minus 5 into x minus 2 all squared. So this becomes the moment equation. Now recall from bending equation, okay, from bending equation, all right, so we simply have that the flexural rigidity, which is EI, double derivative, the square y all over the x squared, is simply equal to moment about the section. So it simply means, in place of this mxx, we'll simply replace with this value, and then we can integrate to find the slope equation and the deflection equation. All right, so that simply means EI d squared y over the x squared is now equal to, so in place of mxx, we simply put in the value for this moment. That's simply 20x, okay, Macaulay's bracket, minus 20 into x minus 1, okay, Macaulay's bracket into minus 5 into x minus 2, okay, yeah, minus 2 all squared. All right, so we'll have this. So to obtain the slope equation, we actually what? Integrate. So integrating, we have of course, if you integrate the square y over the x square, that simply gives us dy. So this is ei dy all over the x. And this is now equal to, so you integrate x here, you have 20. If I integrate x, I will simply have x squared all over 2 plus, I said as well, you put in the constant of integration after the Macaulay's bracket and not after the Macaulay's bracket. So here we'll introduce our constant C1, which is a constant for the first integration. You put down your Macaulay's bracket, and I said to integrate this function x minus 1 from Macaulay's theorem, you integrate it as if you're integrating a single variable function. So this is simply going to give us minus 20 into x minus 1 all squared all over 2. Just like the way you integrated x squared here, sorry, x here, and you had x squared over 2. You also integrate x minus 1 as a single variable function. That simply gives us x minus 1 all squared all over 2. Okay, finally, the last Macaulay's bracket, we have minus 5, okay, into same thing here. You integrate this function as a single variable function. Now we have x minus 2 squared. So which means if we're integrating this, we're simply going to have x minus 2 cubed all over 3. Because from the law of integration, you simply add 1 to the power, then divide by the sum of the one you added to the power and the power. That simply gives you this, okay? So this is called the slope equation. Okay, so rearranging this equation, we are simply going to have ei dy the to be equal to, so I will simply have here 20 can divide 2 here. That simply gives me 10x squared plus c1, okay, Macaulay's bracket. I have here 20 divided by 2 here, also gives me minus 10 into x minus 1 all squared, okay, and finally the last Macaulay's bracket here, I have here to be minus 5 all over 3, okay, into x minus 2 to the power of 3. So I have this, okay. Next up now is to integrate further. Further integration gives me the deflection equation. If I integrate the y dx, I will simply have y, which is the deflection equation. So let's try it and see. So integrating again, we are going to now have, if I integrate the y dx with respect to x, automatically it becomes y. That's the deflection. So that will simply give me e I y, and that's equal to, here I have 10, okay. Now if I integrate x squared, I will simply have x to the power of 3 all over 3, okay, plus, to integrate a constant now, here is c1 with respect to x. To integrate a constant, simply attach the integral variable to what? The constant. That gives you the value of the integration. So to integrate c1 with respect to x, I will simply have c1x. So, okay, but since I carried out a second integration, it means I have to introduce my second integral constant. So I will simply have plus c2, which is the second integral constant. Okay, so after that, okay, so I will introduce my Macaulay's brackets. I simply have the bar, okay. Now I have minus 10 into x minus 2 all squared. I need to now integrate x minus 2 all squared. And I said to integrate this function inside the Macaulay's bracket, consider it as what? A single variable. The same way you integrated x squared and you had x cubed all over 3, that's the same way you're going to integrate x minus 1 all squared. You consider it as a single variable. And if you do that, you have, first of all, put down your minus 10. So if you integrate x minus 1 squared, you simply have x minus 1 to the power of 3 all over 3. Okay, put down your Macaulay's bracket. Same thing applies here. Here I have minus 5 over 3, put it down, minus 5 all over 3. Now I need to integrate x minus 2 to the power of 3. Still consider it what as a single variable and integrate. Okay, that will simply give us x minus 2, okay, to the power of 4 all over 4. So I'll simply have this. Okay, just to break this equation a bit, we'll obtain that ei y is now equal to, of course, here 10 divided by 3 gives us 3.3 approximately. So you have 3.3 x cubed plus this is c1x plus this is c2. Okay, put down your Macaulay's bracket. Same thing here. Minus 10 divided by 3 gives us minus 3.3. Okay, into x minus 1 to the power of 3. Put down your Macaulay's bracket. Same thing here. Here I have 3 multiplied by 4, and that's simply 12. So this is simply minus 5 all over 12 into x minus 2 to the power of 4. Okay, so you have that. So this is called the slope equation. All we need to do at this point is simply find the value of the constants C1 and C2. And I said to do this, we simply employ boundary conditions. Now, what are the boundary conditions? We have basically what? Two boundary conditions. The first boundary condition is we are at point A, which is at the beginning of the beam. You take boundary conditions at that point. Second boundary condition is simply we are at the end of the beam, which is simply at point B. Okay, so let's start with the first boundary condition. Consider at point A. At A, okay, x is equal to 0 because x actually started from point A down to where the point of section. So since it starts at point A, it means directly at point A, the value of x does not exist. So x is actually 0. Same thing here. I have a load of 20 kilonewtons at point A. So which means at this point, a deflection cannot occur because any form of deflection, this load would counteract it. Okay. So I'll simply have that at that point, deflection y is also 0. At point A, deflection y is also 0. So if I put in this 2 now into the equation, I will simply obtain ei in place of y now. Y is simply 0. So it becomes times 0. And this is equal to 3.3 in place of x cubed. X is 0. So I will simply have 0 all cube, okay, plus c1 in place of x. X is also 0, so I'll simply have times 0 plus c2. Now put down your Macaulay's bracket. Here I have minus 3.3 into x. Here is 0, so it simply becomes 0 minus 1 to the power of 3. Put down your Macaulay's bracket. I have here minus 5 all over 12 into x. Here is 0. So this simply gives me 0 minus 2 to the power of 4. Okay, so I have this. Okay. Alright, so from here now, ei times 0 simply gives us 0. Of course, everything multiplies 0 here simply gives us 0. I have 0 is equal to, same thing applies here, 3.3 times 0 also gives me 0. Okay, plus here I have c1 times 0 also gives me 0. Okay, plus c2. Okay, so put down your Macaulay's bracket. Here I have minus 3.3. Okay, into 0 minus 1 simply gives me minus 1 to the power of 2. Okay, put down your Macaulay's bracket. Here I have minus 5 over 12. Okay, into 0 minus 2 simply gives me minus 2 all to the power of 4. Okay, now the rule says, according to Macaulay, every value inside the Macaulay's bracket that is less than 1 automatically becomes 0. So if I take a look at the Macaulay's bracket, I have minus 1 here, and minus 1 is less than 1. So automatically everything in this bracket becomes 0. Same thing here. I have minus 2 here, and minus 2 is also what? Less than 0. So everything in this bracket automatically becomes 0. So those two are off. So it simply means that is now equal to, simply 0 is equal to, here 0 plus 0 is still 0, plus C2, so I'm left with plus C2. Okay, C2, since everything here is 0 automatically, this actually implies that C2 is equal to 0. So if C2 is 0, we simply substitute into what? The deflection equation for C2 in place of C2 here. Therefore, the equation becomes, okay, the deflection equation becomes, okay, the deflection equation becomes EIY equal to, here we have 3.3 x cubed, 3.3 x cubed, okay, plus C1x plus C1x. Of course, the value of C2 is 0, so that one is off. So you put down your Macaulay's brackets, minus 3.3 into x minus 1 all squared. Okay. Okay, sorry, all cube. All cube. All right. And finally, put down your second Macaulay's brackets. Here we have minus 5 over 12 into x minus 2 minus 5 over 12 into x minus 2 all to the power of 4. So we have this. Okay, so to obtain the first constant of integration, that's C1, we also take boundary conditions. Now, the second boundary condition, remember I said we are taking two boundary conditions. First at point A, which have been done, that's at the beginning of the beam, and next at the end of the beam, which is simply what? Point B. So at point B, x becomes total length from point A down to point B. Remember, we took a section here from A to the point of section, we called it x. Now at B, x actually extends from point A down to point B, which simply becomes total length of the beam from A to B. And that's simply 1 plus 1 plus 1 plus 1, which is simply 4 meters. So the total length is 4 meters. So x is equal to 4 at point B. Also, at that point, there is no deflection. Take note, at point B, there is no deflection because we have the 20 kilonewtons force acting upwards. This force will actually counterbalance what any form of deflection. So at B, there is no deflection. Y equals 0 at that point. So Y equals 0. So you simply have this. Okay, so therefore, let's substitute these conditions now into the slope equation. So in place of y simply is 0. We simply have EI, okay, times 0 equal to, this is now 3.3 into, in place of x now, x is 4. It becomes 4 to the power of 3, okay, plus C1 times x is 4, okay, times 4. Open your Macaulay's bracket. You have here minus 3.3 into x here now is 4. That's simply 4 minus 1 to the power of 3. Open your final Macaulay's bracket. Okay, we have minus 5 all over 12 into x is simply 4. So that's 4 minus 2 to the power of 4. So we simply have this. Okay. Of course, EI times 0 here simply gives us 0. And this is equal to, this is simply 3.3 multiplied by 4 to the power of 3 is simply 64. Okay, plus this becomes 4 times C1, which is simply 4 C1. So open your Macaulay's bracket. Here we have minus 3.3 into 4 minus 1 here is 3 to the power of 3. Okay, put down your final Macaulay's bracket. We have minus 5 all over 12 here into 4 minus 2 here is 2 into to the power of 4. So you have this. Okay, so here we simply have 0 is now equal to 3.3 by 64 We have 211.2, okay, plus 4C1. All right, so if we look at the Macaulay's bracket now, the values inside are greater than 1, so we can simply take it off now. So we simply have minus 3.3 into 3 to the power of 3 is 27. 27, okay, minus, we have here 5 over 12, 5 all over 12 into, of course, 2 to the power of 4 is 16. So you have 16, all right. So therefore 0 is equal to 211.2 plus 4C1 minus 3.3 by 27. So that gives us minus 79.2 minus, please, 5 over 12, 0.42 multiplied by 16. Okay, so we simply have 0 equals 211.2 plus 4C1 minus 79.2 minus 0.42 times 16, 6.72. Okay, so at this point, all we need to do is simply collect like terms. So 0 is now equal to 211.2. So let's simply send minus 79.2 and minus 6.72 as a form of collecting like terms. So we simply have minus 79.2 minus 6.72 plus 4C1. All right, so we'll simply have this. 0 is now equal to 211.2 minus 79.2 minus 6.72. So we'll have 125.28 plus 4C1. So at this point, all we need to do is simply send 125.28 over to this side of the equation. Positive sign crosses an equal to sign becomes negative. So we'll simply have minus 125.28 equals 4C1. So we can make C1 subject by simply dividing through by the coefficient of C1, which is simply 4. Okay. Let's do that over here. All right, so it means C1 is actually 125.28 divided by 4. 125.28 divided by 4. This implies C1 minus 125.28, please. So C1 equals minus 31.32. Okay, C1 equals minus 31.32. So if we have, all right, so we have the value of C1 now. We can now substitute into the deflection equation here to obtain the real deflection equation. So we simply have EI equals 3.3 x cubed plus C1x here, but C1 is simply minus 31.2. C1 is simply minus 31.2. Okay, 32. Okay, so in place of C1, I will simply have minus 31.32x. Put down your x, okay? You open your Macaulay's bracket, so we simply have minus 3.3 into x minus 1 to the power of 3, and then final Macaulay's bracket we'll have here minus 5 divided by 12 actually gave us 0.42. Okay, so minus 5 divided by 12 here gave us minus 0.42 into x minus 2 to the power of 4. This is cool. The first question says we should find deflection at point C. Now, to find deflection at point C is simple. It's simply saying at point C, what is the value of x? Since x runs from point A down towards the point of section, now we want to find at point C, what is the value of x? Simply note that from A to C, x is simply what? 1 plus 1, which is actually 2 meters. So at C, the value of x is simply 2 meters. Therefore, deflection of C can be given as at C, x equals 2 meters. That is total distance from point A down to point C. Now, the deflection at that point, y can simply be called yc. Okay, y can simply be called yc, where yc simply means deflection at point C. Okay, so we simply have this. This is EIY. We simply have this to be EI YC equals, okay, so this is 3.3. 0.3 in place of x cubed. Now x at point C is simply 2 meters, so in place of x we simply put in the value as 2 to the power of 3 minus 31.32. okay, in place of x we simply put in the value as 2, so times 2. Open your Macaulay's bracket. Here we have minus 3.3. okay, in place of x here, x is 2, so it becomes 2 minus 1 all to the power of 3. And finally, final Macaulay's bracket will have minus 0.42 here into x here is 2. Okay, so in place of x here, we'll simply put 2 minus 2. So we have this. Okay. Okay, so we simply have here EI YC is now equal to this 3.3. okay, 3.3 here, 2 to the power of 3 is simply 8 times 8. okay, minus here we have 31.32 multiplied by 2, that should be 63. Yeah, 31.32 multiplied by 2, 62.64. yeah, so you have minus 62.64. so you open your Macaulay's bracket. Here we have minus 3.3 minus 3.3 into x here is 2, 2 minus 1 here is 1, so 1 to the power of 3. Open your Macaulay's bracket. Here we have minus 0.42, 2 minus 2 here is 0, so we have minus 0.42 multiplied by 0 to the power of 4. okay, to the power of 4. So EI YC is now equal to 3.3 multiplied by 8. We have 26.4 minus 62.64. Of course, in this Macaulay's bracket now, we have positive value. So that means it's going to hold. We need to take off the bracket now. So it becomes 1 cube is still 1. So we simply have minus 3.3 times 1 still gives us minus 3.3. Here we have 2 minus 2, which is 0. So automatically everything here is 0. That's off. So EI YC is now equal to 26.4 minus 62.64 minus 3.3. Okay, so we have minus 39.54. 39 or 31? Okay. Alright, so to make YC subject, which is deflection at point C, we simply divide both sides by the flexural rigidity, which is EI. So this simply implies that YC is simply minus 39.54 all over EI, which is the flexural rigidity. And from the question, the values of E and I was given. Okay, the values of E and I was given. Okay, E is simply, E was given as 200 by 10 to the power of 6 kilonewtons per meter squared. Okay, so we are giving E as simply 200 to the power times 10 to the power of 6 kilonewtons per meter squared. We're also giving I from the question. I was given as 20 times 10 to the power of minus 6. Okay, minus 6 meters 4. So we can simply compute this. This becomes minus 39.54 all over, in place of E, which is the Young's modulus, value is this 200 by 10 to the power of 6. We simply have 200 by 10 to the power of 6. Not also forgetting, it is in kilonewtons per meter. So converting kilo means times 10 to the power of 3. Okay, multiplying by the moment of inertia itself, which is 200 by 10 to the power of minus 6. So you simply have times 200 by 10 to the power of minus 6. Okay. All right. So YC is now equal to minus 39.54 all over. So you give me 200 exponential 6 multiplies exponential 3 multiplies 200 exponential minus 6. 200 exponential 3, 200 exponential 6 exponential 3 multiplies 200 exponential minus 6 simply gives us 40 million, which is 40 by 10 to the power of 6. So therefore, minus 39.54 divides 40 exponential 6. This simply implies YC is equal to, so the value is minus 9.885 by 10 to the power of minus 7 in meters. So this becomes the value for the deflection at point C. Okay, so that's that for deflection at point C.